Welcome back. From our previous video, we were looking at uniform circular motion, and we looked at the definition of circular motion. We also looked at examples, and in this video, we are going to continue further. And our last definition in the last video was uniform circular motion, and we agreed that it occurs in bodies that are moving in a circular path at a constant speed. Now, I wanted us to have a note on the clip above that uniform circular motion occurs in bodies that are moving at constant speed. Now, constant speed here does not necessarily mean that the acceleration is zero. Actually, from linear motion in Form 3, we realize that acceleration is gotten as final velocity, u minus initial velocity, you divide by the time taken. And then in our case, since the speed is constant, it means that the final is the same as the initial, and if you subtract the two, the difference is zero. Now, if you divide it by time, you'll get just zero, so acceleration is zero. That is according to linear velocity, that is linear motion we tackled in Form 3. But in this case, we want to note that since the body is moving and there is that change in velocity and time. Now, somebody may ask how velocity is changing, and we agreed the speed is constant. Remember, speed is a scalar quantity, and the velocity is a vector quantity. Speed is a scalar quantity. Velocity is a it is a vector quantity. Velocity has both direction and magnitude, so you can state that the velocity of a vehicle is 20 meters per second, and it's heading north, or it's heading south, or it is heading, or it is 36 degrees north of something. So velocity has direction, whereas speed has no direction. Now, and you realize that when the body is rotating round a circular bath, it means that at certain instants it will be having different velocities. It can be the same magnitude, but it will be different in terms of direction, because at a certain time it can be north, at a certain time it can be south. So that's why I wanted us to note that the body is accelerating. So never say that the acceleration is zero, because you can argue from the point in linear motion in Form 3, that is topic 1. You can argue and you will be right. But in this case, I'm saying that velocity, it will be changing due to change in direction, because when you're moving around, you will not be at the same instant, or you will not be at the same point every time. So recognize that even though a body is in circular motion, may have a constant speed, its velocity is changing, and hence it is accelerating, and I've argued on the same. Now, also, let's look at the definition of angular displacement. And when a body is moving around a path that is round, like in the figure shown, this is a circle of center O. We are assuming that the body is moving along the circumference of that circle, that is this point here. Yeah, it's moving around here. So in the process, it will be tracing a path that is round. The center is O, the radius is A. Now, let's assume that the body has moved from point A to B as shown below, and the angle that is covered, that is theta. Remember, AB is just an arc, and an arc of a circle, from the definition of circles, we know that an arc is a part or just a portion of the circumference of a circle. Now, a small part of the circumference is just an arc. Now, the arc AB, it can be the minor and the major arc. It depends on what you are looking at. But with me, I'm looking at the minor arc, that is AB, that is AOB, the minor arc. Take note of that. I'm using the minor arc AOB, and the body that is moving from A to B, it is tracing a path that is A to B, that is, we call it arc length AB. Now, if somebody looks it from another point or from another angle, that it is tracing an angle theta at the center. In other words, the arc length AB is subtending an angle theta at the circumference, not at the circumference, but at the center. Let me repeat it, that the arc length AB is subtending an angle theta at the center. Now, the angle subtended at the center, that is angle theta, it is our displacement. Now, angular displacement is defined as the angle through which an object moves on a circular path, the angle. Now, in another definition that is more convenient, we'll be using the angles should be in radians. So in this case, you have to take note of that the angular displacement, the angle should be in radians. So the SI unit of angular displacement is radians. Take note of that, that the SI unit of angular displacement is in radians. Now, after looking at the angular displacement, I will be taking the side, that is from this circle. You see that we have AB. AB, in this case, I'm taking it to be S. Remember, we represent distance in mathematics in physics, as S, but in mathematics we use D. But in this case, I'll be using S, and the radius of the circle or the path traced to be R. I'm saying that I'm using the S to represent the distance covered, that is AB, or you can see at this clip that AB, that is the distance, and I'm representing it by letter S, and the radius is R, and my angle theta, I'm taking that it is S over R. Now, I want us to do some symbol calculations or derivations. Now, assume that you have a circle. Take your pen and write somewhere, and assume that you have a circle of radius O. Assume that you have a circle of center O and radius R. Now, from from Form 1 and the length, you can find the circumference, that is C, to be is equals to 2 pi R, that is the circumference. Now, if I want to find the length AB, that's an arc length. How to find the length of a sector? I think AOB, it's a sector of a circle. Now, how to find the length of that sector? We just take the length, that is L, is equals to theta, that is the angle subtended at the center. You divide by 360, that is the angles at a point. Then you multiply by the circumference, that is 2 pi R. In other words, length is equals to theta over 360. You multiply by 2 pi R, and where R is the radius, L is the length. Now, I want us to make theta the subject of the formula. I think you've done it in Form 3, that is formula and variations. Now, make theta the subject. It will be theta is equals to the length. You multiply by 360. You divide by 2 pi R. Theta is equals to L. L is the length. You multiply by 360, 2 pi R. But But L, in our case, that is from A to B, we are using letter S, that is the distance. In other words, our theta is equals to S, you multiply by 360 over 2 pi r. Now, 2 pi, we want to see that 360, you divide by 2 pi, it is just 1 radian. 1 radian. 360 you divide by 2 pi is 1 radian. In other words, our theta will turn to be S you divide by r, because I'm assuming that 360 over 2 pi is 1 radian, and then our theta becomes S over r because 360 over 2 pi is just 1. Then theta will be, our theta will be S over r. That's what we were doing here in this one. So we said theta in radians is S over r, and I have derived the same. I've said that you take the length of the sector A or B. To find the length, you just take theta over 360 to pi r, and then make theta the subject of the formula. Then you get that S is that theta is S times 360. S is 360 over 2 pi r. Now, 360 over 2 pi is just 1 radian. In other words, for you to cover the whole of the circle, you would have covered 360 degrees. And then taking 360 over 2 pi to be 1 radian, then theta in radians is S over r. Now, you may be asked to give the definition of radian angles. Now, radian angles, we may take it as 1 radian is the measure of the central angle whose arc length is the same as the radius of the circle. That is to say 1 radian. I think there's an error in typing here. It's supposed to be 1 radian. 1 radian, you just write 1, then superscript C. So that is 1 radian, 1 superscript C, radian denoted as 1. There's also 1 here, supposed to be 1. It's supposed to be 1. I'm writing here, subscript that way. I've written somewhere there. So it's 1 radian is equals to 57.295. Or for you to get it, you can take just the total angle at a point is 360 divided by 2 pi. Now 1 radian is 57.295 degrees. So here it's supposed to be degrees, 57.295 degrees. Take also that correction. Then also, after finding the radian angles, and then we have, now you see how we can represent our angular displacement. We are done with the definition of radian angles. Let's see the linear velocity. Somebody may ask us why I'm finding the definition of linear velocity in this point, but it is so important because it is going to help us to represent angular velocity in form of linear velocity. So our linear velocity from form 3 we agreed is that you take the change of displacement, you divide it by change in time. In other words, it's the rate of change of displacement of an object that is traveling along a straight line. Now, in linear velocity, it is traveling along a straight line, and in angular motion or in circular motion, we agreed it is traveling in a circular path. Take that note also that in linear velocity, the object or the body is moving in a straight path, whereas in angular velocity or in circular motion, the body or the object is moving in a curved or in a round path, in a circular path. Now, in linear velocity, we can represent it that way, that the velocity v, we're going to use letter v in this case to represent the velocity, that's linear velocity. Now, if we are going to calculate angular velocity, we will not be using v. Wherever you will be seeing letter v, it will be representing linear velocity. Now, linear velocity is just change in displacement, and in my previous clip I said that S will be representing displacement, or rather distance. It's the same thing. So in our velocity, it will be change in velocity, you divide change in displacement, sorry, you divide by change in time. That is our linear velocity. We'll use it. That's why I'm bringing it in now. Now we can go to angular velocity. Sorry, in angular velocity. Now, from linear velocity, we've agreed that is the change in displacement, that is change in displacement, you divide by change in time, you get your linear velocity. Linear velocity. Now, in angular velocity, it is the same thing, but now it will be the change in angular displacement. You divide by change in time, and this time round, the vehicle or the body or the object will be moving around a circular path. Now we'll be representing angular velocity as omega. Let me write somewhere here. It will be omega. I'll be using omega to represent angular velocity. Now angular velocity omega, it will be the change in angular displacement, you divide by the change in time. And the angular displacement, if you remember, we agreed we are going to use letter theta here. Let me remind you, we'll be using theta here. It is here. So we'll be using theta to represent angular displacement. We are using S to represent our angular displacement. Not angular displacement, but our distance, that is the arc length, and also the radius is just a constant. We'll be using it for the distance from the center to the circumference. Now the angular velocity, we are going to use omega, and the omega in this case we are going to use the change in displacement, you divide by the change in time. It is here. For a big change, that is, we are using a triangle for the big change, we are getting theta over t is equals to omega, and the omega we are agreeing that is the angular velocity. Now from equation where we were using theta, that is our angular displacement, to be the arc length, you divide by the radius. From here, I think, yeah, this from here, here. This is our equation 1, where we are seeing that theta is equals to S over R, and we are agreeing that S is our arc length. We divide by the radius. Is our equation 1, and we want to use it here. Then omega, it is S over theta. Now look at this omega here. Look at this omega here. This omega has theta here. Now this theta over, we want to replace theta by S over R from equation 1. I think you know equation 1. Equation 1 was under the representation of angular displacement. Now we want to remove that theta. We replace it by S, you divide by R. Then it will be in the form of this one here. It will be omega is equals to S over R T. That is S over RT. Now for small changes, we normally use sigma, but in this time I'm using these small triangles to see a change. For small changes, that is change in angular displacement, you divide by change in time, you'll get that it is change in that is the arc length, you divide by R, change in time. Now somebody may ask, why is it that we don't use the change in R? R is a constant. Remember, you can't say that the radius of a path changes. We normally trace the radius to be the same. In other words, R is a constant. R is uniform. R does not change. and that's why I've not used change in r. I've just said change in s, you divide by r, change in t. Remember, radius is uniform, that is constant. I've noted here, that is good of it. Now from linear velocity, we know that velocity is change in s, you divide by change in t. Now I want you to see this part here, that is change in s or change in t is the same as here. Now with me, I can replace it direct. Then I'll get change in theta over change in t. We'll get v over r. Now that becomes my omega is equals to phi over r, and that is the representation of angular velocity in form of in linear velocity. Now in this case, I'm representing omega in two ways. Now in case you are not given the radians, that is angle in the radians, you are not given, then it means that you are going to represent it in you are going to use the linear velocity. If you have the radius, then you get omega. So there are two ways to get omega. Omega is the angular velocity. One way we'll use the radians here. We'll use the radians. Then we divide it by the time given, or the change in time. That's one way. Another way, it will be angular velocity. Angular velocity is equals to linear velocity, that is v. You divide by r, and I've shown how we can derive it. Thank you for watching. Let's meet in the next clip.